Then let us have a look at sequential logic optimization techniques that are possible. So again, in sequential logic optimization, there are two techniques. One is the basic one and other one is the advanced one. So in the basic one is sequential constant propagation. So we will see what is a sequential constant propagation. This is very much covered in this uh, discussion and subsequent labs also. And advanced techniques which are not covered as part of lab, but we will quickly touch the theoretical concept as part of the theory here, but it's not covered as part of lab. That is like state optimization, something called as retiming, and also something called as sequential logic cloning. So I'll give you quickly aware of the awareness to all these topics, but these are not covered as part of lab. But sequential logic constant propagation is covered as part of lab. Okay, so let's have a quick look at what is sequential constant. Okay, sequential constant. Now let's say I have a flop and its D input is tied low and I have a reset connected to it. Okay. Now, if you look at this flop, now, is there any possibility when Q will become 1? Let's say, for example, I have a logic connected like this. Say it's connected to another pin called A, and this is connected to, say, an inverter here, sorry, NAND gate, and you have a Y here. Okay. Now, let's quickly look at this. Is there any way where this Q can become 1? So whenever either the reset is applied or the clock is ticking for a flop, correct? If reset is applied, Q is 0. If there is a reset, Q equal to 0. If there is no reset, if reset is not there, then also Q equal to 0 because D is equal to 0, correct? So Q is always 0 whether I apply reset or whether I apply a clock. Whether I apply a clock or whether I apply a reset, Q is always 0. Now this 0 sort of propagates down and this becomes A dot 0 the whole bar, which is A bar plus 0 bar, which is A bar plus 1, which is always 1. So Y is always 1 irrespective of clock, reset, Q, A, anything. For this, Y is always 1, and that happened because of the sequential constant. So effectively, if you see, I don't need any of these gates, Y will be equal to 1 always. So this is an example of sequential constant propagation. Now there's a very interesting point I want you guys to note here. Let's say for sake of argument, I have a set flop connected here. This is a set flop connected here and D is connected to 0 and I have a Q, I have a clock. Now let's say the rest of the logic is same. Now here, kindly pay attention. When set is applied, Q will be 1. When set is not applied and there is a clock, Q will be 0. That means Q is taking the value of both 0 and 1. So you don't know when Q is going to become 1, when Q is going to become 0. Okay. So, and I cannot simply connect set bar. Many people get confused. Why can't I put Q as? Can I say Q is equal to set bar here? Can I say this? The answer is no. It's a very, very interesting thing. Let us look at the timing diagram here. This is going to give a lot of insight to it. Let's say this is my clock. This is my clock. And let's say this is my D input is always 0, so I don't care about it. And my set signal looks something like this. So let us look at how Q is going to look. How Q is going to look, because set is 1 here, irrespective of set is like a asynchronous input, I don't wait for clock. So Q is 1. Now set goes 0 here. Now set goes 0, or can I say Q equal to set bar, or not set bar exactly here, sorry. Can I say Q is equal to set? Not set bar, Q is equal to set. Can I say that? The answer is no. Okay, let's see why. Now I am removing set here. If Q is equal to set, Q should have followed set, right? But that's not the way it's going to be. Now when set is removed, the asynchronous input is removed. But set is removed does not mean the flop will go, Q will go to 0. It is going to wait for the next clock edge to follow D. So in this next clock edge, Q will go 0. So there is a clock cycle delay here. So Q goes 1 asynchronously, but Q goes 0 synchronous with respect to the clock. So I cannot simply say Q is equal to set, because while set is going 1, Q instantaneously goes, whereas when set is going to 0, Q is sort of waiting for the clock to become 0. So I cannot say Q is equal to set. I cannot say this. Okay, this is a very important point. That means this flop here cannot be optimized. It needs to be retained. If this flop needs to be retained, this sequential constant cannot propagate. So this logic cannot be optimized. This whole logic will be retained as such. So kindly note, every flop with D input tied off is not a sequential constant. For the flop to become sequential constant, the Q pin should always take a constant value. Here the Q pin, whether you apply reset, whether you apply a clock, whatever you do is taking a constant value. So this is a sequential constant. Whereas here the Q pin is not taking a constant value. It can take both 0 or 1 depending upon the nature of set or the nature of clock. So here the flop needs to be retained in the circuit. Okay, so this is not a sequential constant. This is very, very important point. Okay, this we will discuss in labs. Don't worry about this. We can see this optimization techniques in action in labs. So other than that, there are few other things which I will sort of throw light upon, but we will not be having labs for it. That's called as, let's say, state optimization. Then we have something called as cloning. We have something called as what are the techniques we mentioned here? Retiming, correct? Retiming. We'll look at retiming also.